Today we're going to be talking about polar equations and what polar coordinates and everything are. So the Cartesian coordinate system, or the rectangular coordinate system, I'll say both between different things, are your regular system that we've done before we know. It looks like this. It's your x and y. This is what you've been graphing things on forever, blah, 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 blah. So what we're doing today is the polar coordinate system. And if we were in school, this would be like my favorite day of notes because it's all new and fun graphs. But now I'm just going to talk to myself. But the polar system here uses direction and distance to give you your coordinates rather than like x, y. So you use your radius, like how far are you out from the center, and what angle are you at. So this works good for like sonar and different things where you're not really on an xy coordinate plane. So a note here, points are written as r theta. So if you can see this little dot right there, this point could be written as 1, 2, 3, 4, 5 radiuses out at an angle of pi over 3. A note, unlike Cartesian coordinates where there's only one name for a point, polar coordinates can have multiple names. So like this point right here, if I graph it, you go to 7 pi over 4 and go out 2 radiuses, we're right there. But I could also call 7 pi over 4 negative pi over 4 and it would give me the same point. Or if I go to 3 pi over 4, instead of counting out positive radiuses towards my angle, I could count negative radiuses and end up at the same point. So there's an infinite number of ways to name polar coordinates. Why do we care about polar coordinates? Why do we use them? So first one is when distance and direction are more important than other things. So sonar and that, like tracking that kind of stuff. And kind of like parametric, there's some graphs, some things that are really complicated in your standard Cartesian coordinates, but are pretty easy in polar coordinates. If you'd like, on Schoology, there's a polar battleship you can play. So it looks like this. You set up your ships and you play like regular battleship. But here's a note. Polar equations are usually written with r equals something in terms of theta. So like normally you have like y equals something with x in it. Polar coordinates, you want r equals something with theta in it. How do you graph them? So like we did before when we switched into parametric equations, it's going to be similar to get to polar. So go to your mode. Again, you want to be in radians, and then we want to have polar selected. So arrow down, over to polar, hit enter, and then you can do second quit to get out of that. Okay, and make sure you're in radians. So if you're ever graphing polar stuff and it's not working, make sure you're in radians first. So these, I'll do one with you and walk you through graphing all of them, but then I'll have to graph the rest at home, just so I'm not spending a ton of time typing stuff in since it's slow on my calculator. So to do this, we go to the window. Theta, again, is just going to be this xt button, and then sine of theta, and then go to your window to enter all the window stuff, so 0, and then 5 pi, and 0.1, negative 15, positive 15, 5, same idea, negative 15, positive 15, and 5. And then hit graph. And this is the graph you get. So pretty cool looking, in my opinion. So now go through and change the theta step to all these different things and see what happens. Okay, so I'll do like a middle one just so you can see it. If I go here and change this theta step to 1.5, and hit graph, your graph is going to get a lot messier and not look like it's supposed to. You don't get your nice spirals. Now, if I go in and change it to something like pi over 3 and hit graph, you lose your spiraliness. Like you get the same general shape, but it's all pointy. So what that means, or the lesson from this, is that the smaller your theta step is, the longer it's going to take for your calculator to graph it because it's plugging in like smaller increments. So I usually do 0.1 because it's enough detail you can see what's happening, but it's not so small that it's going to take forever to graph. And then avoid steps that have pi in it because those give you the weird like sharp angles instead of like nice curves. Okay, so graph this one and change your theta max to 2 pi, 3 pi, 4 pi, 5 pi, etc. Okay, so as you increase this, your spiral is going to keep going farther and farther and farther. So you're adding more and more to your graph. Now graph this one and look at the graph. Okay, so if you get to 2 pi, you're going to get an 8-sided flower. We'll try and draw this. Kind of like that. So it's kind of messy. And then as you keep going up, you just draw over that same flower and over again. So the lesson from this is some polar graphs loop over themselves, some don't. So generally start with your theta max going to 2 pi, so 0 to 2 pi. Sometimes you'll have to get bigger than that, but this idea is coming from standard trig functions, usually have a period of 2 pi. Okay, so graph this one and then hit zoom square. So if you just normally graph it, you'll get an oval. If you hit zoom square, you'll get the circle. The lesson from this is your calculator window is a rectangle, so it stretches everything out to be rectangular. But if you want it to be square, you can hit zoom square. So your image is going to be a little stretched out when you look at them. And that's it. Your assignment's on Schoology.